All right. Happy Monday. We're already, I think I put the wrong week now in the stream. We're at week like 7, right? Aren't we? I think I put week 6 in the stream accidentally. Week 7. Oops, time is flying by. So yeah, we're almost barreling towards the end. I feel like a couple of announcements. So your Blackboard grade, I mean, I always tell you that your Blackboard grade is inaccurate, but Blackboard has really gone off the rails today. Oh, sorry, let me fix my mapping on my tablet. There we go. All right, so your Blackboard grade is crazy. So I'll just say Blackboard inaccurate. I mean, it's always inaccurate, but I got a lot of emails saying that like their quizzes had been changed to a total of 15 and now all of you are failing even though there's only 10 questions. I have no idea why Blackboard has done this. It is never, I mean, it's always been like inaccurate, but now it's, I don't know where it got this point value from. So that's why I always calculate your grade manually myself. So I put it into Excel. You have the syllabus. So we can pull up the syllabus. And right, so you could calculate your grade yourself. And like I mentioned, I'll take this exam down to 40% and then give people just 10% free credit, right, for helping with the My Open Math. So even if you've done just a few assignments in there, that can change your percentage. And again, it's just like a bonus. Thank you for putting up with the My Open Math chaos and now the Blackboard chaos. So again, that's how your grade is going to be calculated. I'm going to do it manually on Excel by myself, certainly not with Blackboard's help because it is gone off the rails. So yeah, ignore Blackboard. Like in years past too, I've had it like give half the class A's and half the class F's and like no clue why it does that. So yeah, I do not trust Blackboard. And then I think I've tried to make this clear, but right, I have a lot of people mixing and matching modalities. So wherever you want to take the exam, you just need one exam, right? So if you took it in person, you're fine. If you took it online, you're fine. If you took it both just to try it, great, but I don't need, 2 copies. So again, your Blackboard is freaking out on itself, and I've given up on Blackboard for now until I at least rebuild the whole thing in My Open Math. And so that being said, I did manage to at least put something up for chapter 5 then. So the quiz is up and the homework is up on My Open Math. So the quiz for chapter 5 will be this Wednesday. So if you want to take the quiz online or both, like I said, that works great for me. And then just give me until Wednesday until you yell at me about grades again. I'm working. I did a bunch of in-person grading, so I just need to like put them in the grade book. So that's kind of in progress. So like I said, hopefully by Wednesday, everything will have gotten back. And then if you're still missing stuff or things are like missing on Blackboard, then just let me know. But like I said, I know that the totals are all crazy. I'm not looking at the totals, just the points when I go do it myself. Other kind of questions, comments? I have to shut the door. All right, so let's, like I kind of teased last week, so I said we're going to leave redox reactions, at least kind of the nitty gritty, for the start of this week. And so now we're here. And so let's go over some redox reactions. And so like we had mentioned, these oxidation reduction or redox, as they're often shortened to, this just means that this is a type of reaction in which electrons are transferred from one reactant to another. And then, right, recall which ones were potentially our redox reactions, right? So maybe our combination. So the hint is we're starting with an element, so two things in their elemental form coming together. We had our redox, our combustion reaction. So any combustion reaction, or maybe, right, we saw the combination as a subset of this type, right, where we're just adding oxygen. So here's another kind of combustion-like reaction. So these combustion reactions, burning with oxygen, adding oxygen, so that's a hint that we have a redox reaction. Or, so not on here, but we went over it last week. What was the other kind of major type of reaction that's usually redox? Yeah, single replacement. And so again, your hint is something in the elemental form going away and making something new in the elemental form. So zinc solid plus our copper sulfate aqueous will then give us zinc sulfate in solution, which was a clear liquid, plus the copper solid metal back out. So good. So those are our main, again, kind of like flags, hint, hint. And again, right, our hint is we are looking for something in its elemental form, or something coming in and out of the elemental form, just like up here, right, creating water in this combustion reaction. Which I realize I failed to do this demo for y'all. I just like tend to forget about demos third quarter because now you're like, don't pair well with my 221. So if you guys want me to blow up some balloons, let me know. Or if you're not that excited, we could also do them in like lab too. Okay, so maybe we should plan for it. Since we have this reaction here, it is pretty exothermic. So maybe we should plan for a demo. Would you guys rather do it like in lab or for lecture demo? Okay, so we could do it in lecture. Yeah, and then we may have to like probably properly go outside for this one, which is why I don't just like do it either on a whim, because we're like kind of tight on space, you know, safety concerns, and you'll kind of see why when we do it. All right, cool. So we'll plan for that for lectures. We'll have a little bit of fun with that. And again, right, elemental form. So we'll see how exothermic this reaction is on Wednesday for lecture. But again, right, two elements coming together to make our new element. So hint of a redox reaction. And so again, we'll see this, and we'll see the fire. Yay. And so kind of the other hint is the addition of oxygen to something, so that tells us that something has undergone a redox. But let's look at kind of our formal definitions. And so like we said, we're exchanging electrons. So if we want to convert a free element into an ion, well, in that case, our free element is going to be losing electrons. And then again, in this redox reaction, you have to have an exchange. So if something is giving electrons, the other is accepting them. And so now we can go through some definitions. So atoms that lose electrons are being oxidized. And so that's oxidation. And then if you gain electrons, that means it's being reduced. So it's a reduction. And so let's go over, you may have heard of these mnemonics before to help you remember. So I'm from Texas originally. You know, they're all about big oil there. So the first mnemonic I have is for oil rig. And so you can remember this by oxidation is losing electrons. Reduction is gaining electrons. All right. And so let's say you don't like the fossil fuel industry, or maybe you just like furry cats better, And so I have this one. And so it depends what your favorite kind of furry large cat is. I used to work for a school where like the mascot was Leo the leopard. But it could be like generic Leo the lion goes grr. And so that's losing electrons is oxidation, and gaining electrons is reduction. So again, copy your favorite one so you can quickly remember on an exam. And so let's kind of go through this example here. And so we haven't quite gotten to the rules, we'll get there. But again, I'll tell you that something in its elemental form has an oxidation state of 0. So then I'll write 0 for sodium. So again, free elemental form. And then it goes to sodium chloride. And then just like we should have labeled on our periodic table, right, we should have a big +1. Did I put a periodic table in these notes? Oh, time to steal a periodic table. Now to find one. Here we go. So right, you should already have your periodic table labeled. If anyone needs a new one, I can always get more too. So okay, you have your periodic table. It has 1 over here, which also reminds us it loses 1 electron, 1 plus oxidation state. I'll label this periodic table really quickly. So 3, then the switch over. So -1, -2, -3 typically. All right, so that helps us. Okay, so back to this. So again, in a typical compound with our sodium alkali metal, so 1 plus, and then chlorine, right? Same thing. It's in our halogens, so it's always -1, again, typically speaking for an ionic compound. All right, now let's kind of go through this. And then so sodium, so we said it went from 0 to 1 plus then. And so it underwent oxidation, right? Oxidation is losing electrons, so it lost electrons. And then the chlorine, so our chlorine again started at 0, elemental form. Now it's -1, so it underwent reduction, right? Reduction is gaining electrons, so it gained those electrons. And then notice if we balance it, so we need to put a 2 here to show, okay, well we have 2 equivalents of sodium, right, to balance out our chlorines to make our sodium chloride. So again, same concepts being reinforced. We have to write our ionic compound correctly first, then we balance it. Then we can double check, are the electrons also balanced? And so yes, we have a 1 electron process, right? But 2 equivalents, and then chlorine, so each one gains 1 electron, but then 2. So there's our 2 electrons there. So again, losing and gaining the same amount. And then other terms, we can add kind of one more term to this. So we can also say that sodium is our reducing agent. So it's basically the thing that does the reducing. So it supplies the electrons. So again, it was oxidized, but it's our reducing agent. And we'll find that most of our alkali metals are reducing agents. And then our chlorine is going to be our oxidizing agent. And so those are things that, again, accept electrons. And if you remember from lab, you had the special symbol of, right, the little fire with the O. Oops, I drew that pretty horribly. But that was our oxidizer symbol. And so, again, those are things that can do oxidizing agents, but they're typically compounds. So chlorine gas or, again, oxygen fluorine, all those things are oxidizing agents, so they can accept those electrons, and then we're going to find they're pretty reactive as well, right? So kind of giving us more hints to the reactivity. Questions so far? And so that's what we're doing, is we're trying to identify either an increase or decrease, basically a change in oxidation state. So we'll typically, like we've already seen, see something in their elemental form. Like in this case, carbon goes from 0 and then +4, which is based off of this sulfur. So sulfur is typically -2. We can go back to the periodic table. So sulfur is in group 6, -2 there. And then go back. So then we need to make our compound match the overall charge. In this case, CS2 is neutral. So then carbon has to be +4. So then we can tell that carbon was formerly oxidized, and then sulfur goes from 0 to 2-, so it gained those electrons, so it was reduced. All right, so now let's get to our rules. And so this is kind of like confusing because it makes this caveat here. And so it does say this, so oxidation states are not ion charges. So that's true. So that's more true though for like organic compounds. So for like, I said that wrong. This is more applicable for covalent compounds like organic molecules. But then ion charges, those are going to be like your ionic compounds. So those would be like a measurable charge, and then they do follow, again, how we've labeled our periodic table. But that's all they mean by that. But like I said, just typically go off the periodic table. It'll usually work out. But let's look at our rules and kind of our priority rules. And so our first kind of rule was what we had said. So anything in its elemental state is an oxidation state of 0. So again, that's just its nature form by itself. So if it's a diatomic or anything else we've seen, right, that would also still apply. And then our second one, so monoatomic ions have an oxidation state equal to their charge. So again, like we find for our ionic compounds, so sodium is always 1+, right? So alkali metals, always 1+. Alkaline earth, 2+, right, etc. And then the sum of our oxidation states has to equal, right, what our sum is. So if it's, let's say, a neutral compound, right, it's going to be 0. Or we should say, well, it kind of mentions it down here in Rule 3b. So, or if it's a polyatomic, right, it equals the charge on our ion there. So I think we've kind of seen that, practiced that before, but all right. And then we kind of have this priority. So again, everything kind of follows. And so let's zoom in on this priority. And so fluorine always takes priority for oxidation state. So this would be more applicable if like fluorine was in a compound with chlorine, right? So then, okay, in that case, give fluorine a -1 oxidation state formally, and then base everything off of that. But again, magnesium's 2+, like we would typically expect here. And then hydrogen is almost always 1+, but there are some exceptions. So anytime we have a metal hydride, I think we saw these metal hydrides with naming, but then our hydrogen is -1 there. So a good example is like aluminum trihydride or boron trihydride. And I didn't draw aluminum very well, right? It should be trigonal planar there. So these hydrides, so again, hydrogen would be -1 in this case. There's also like iron hydrides. And then oxygen is almost always -2. So it's another good one to base your oxidation state off of. But the one exception are peroxides. And so peroxide have this general form of, so let me draw it. And so this R group just means any organic structure. So it could be, let's just look at our simplest one. So hydrogen peroxide, right? That's the thing in the brown bottle. And so that is light sensitive. That's why it's in that brown bottle, right? So I think we mentioned that in lab. So you saw that decomposition on a faster scale, but it will decompose over time. And so these peroxides, typically, I think they're on your polyatomic if I remember correctly, but they're listed something like this. So O2, -2, but notice there's 2 of them. So each oxygen is -1. And so again, they have this structure, so it has to be this oxygen, line oxygen, with any other organic group. And I really do mean any, right? It could be nitrogen. Typically, it'd be some sort of carbon, but there are all sorts of peroxide variations that you can find out there. So again, a chemist is going to want to synthesize everything and anything, and well, chemists continue to synthesize new cool things, so that's why we leave that very open-ended with that R group. So again, any organic group there. And that's really our only exception. So in here, we'll probably only see hydrogen peroxide, but again, just so you're aware of the general peroxide form. And then from that, it basically goes, again, how we expect. So hopefully your periodic table is already annotated like that. So then it follows with the rest. So of course, after taking into account fluorine, then the rest of group 7 can follow. And again, we expect them to be -1 unless we're basing them off of some other element. So with fluorine and then oxygen taking priority in that case. And then same thing, move on to group 6. So we expect them to be -2 unless, you know, they're bonded, again, probably with like fluorine or oxygen. And then nitrogen, again, is typically -5, but it could be, or excuse me, -3, but it could be +5. And so let's look at that actually. And so that's the example given in this polyatomic. So just going through nitrate together. So it has an overall -1 charge. And so we start with our oxygen. So oxygen takes priority. So it's always -2, right? It's not a peroxide. And then we set up our algebra. So -2 times 3, so that's going to be -6. And then so solving for x, so that's how we get +5 for nitrogen in this case, right? Otherwise, again, just goes by our typical what we expect for an ionic compound. So hopefully not like too hard. And we'll keep it relatively basic. And so here's our definition. Again, so like we said, the reactant that reduces the element is our reducing agent. So it was oxidized. And then the reactant that oxidizes our element is our oxidizing agent. And that is reduced. And again, you have your little mnemonics to help you. All right, questions over that one? Let's do a quick example before we kind of transition. This will lead us to our kind of next chapter. And so this is another demo that I've thought about. Well, I've done it uh, for my other class, but it wasn't as spectacular as I had hoped. I'll tell you about the issues. And so while we look at this reaction and what it is, you guys can tell me who was oxidized, who was reduced, and then who's your reducing agent, who's your oxidizing agent. And let me finish writing the reaction. Oops. Help if I could balance it. And so our next chapter is energy. And then does anybody know what this reaction is called? It has a special name. No guesses? I can tell I don't have any pyros in here. Now, so this is the thermite reaction. And so it's super exothermic, so that's why it's famous. And so it was used in building the railroads. And so it's so exothermic that it melts the iron metal. So it's pretty cool. And I did try to do it. I'd actually never done it before. And the first time I did it was this fall, except so kind of the problem with this reaction is just trying to get it to ignite. And so protocols suggest using like a little magnesium stick. Yeah, and it did not want to light my mixture. I was thinking maybe I didn't shake it enough either. So I don't know, I may have to play with it. I did have pyros in my other class that were trying to give me suggestions, or maybe that I was using a bad starter. But yeah, that's this reaction here. So I'm open to doing this one again. Because sometimes if you look at the warning labels of aluminum powder, it does say flammable. So the powder is supposed to be flammable, so I was a little scared to shake it. But I've actually never seen powder light up. But that being said, there's a first time for everything. All right, so who was oxidized, who was reduced? Give you guys a minute or two to look at that. So what oxidation state is aluminum in the beginning? So what about, so it's in its elemental, so what's yeah, 0. And then, yeah, so +3 for the product, good. And then what did iron start off with here as? Oh, sorry, I didn't see how many fingers. Should be 3, right? So iron's always -2, so -2 times 3, so that gives us -6. So iron started as +3, and then what does it go to in its elemental form? So back to 0. Good, okay. So did aluminum lose or gain electrons? So lost, right, because it got more positive. So lost electrons. So then aluminum was oxidized or reduced? So oxidized. So again, it lost electrons. We could say it was our reducing agent. All right, good. So then if aluminum was oxidized, bless you, that means Fe3 plus. And then when we talk about these redox reactions, we usually just focus on the metals. So that's why I'm just going to abbreviate iron 3 plus. So then that means it was reduced. So it gained electrons and then formally the oxidizing agent. All right, questions about that one? I'm watching the chat too. Hopefully the stream should be good. We actually have our Ethernet cable back. All right, so now this brings us to, well, now I realize I don't have the book chapter handy. So I'll try to update the My Open Math. Let me pull up. So it looks like this will be chapter 5 roughly for the OpenStax textbook. So it should pair with thermochemistry. So looking at energy basics. So that's, again, thermochemistry and our OpenStax. So you just have to find any Gen Chem textbook though, right? They're all the same. All right, so we're starting our energy, work, and a little bit of heat. And so let's go through, again, just minor definitions. And so energy just means the capacity to do work. And so energy can be something that an object possesses. So that's kind of the energy that chemistry takes, right? So we're looking at the energy in our bonds. And so kind of, right, the energy in breaking bonds and then regaining the energy in making bonds. And of course, right, you probably are also familiar with energy just going through like physics. So either like exchanging energy through collisions or again, right, like maybe gravitational potential energy. So you could kind of chart the path a ball takes. And so right there's maximum potential energy from gravitational potential energy. Then that gets converted to kinetic energy. So we probably don't need those formulas, but again, just kind of thinking back to other science classes or just kind of other energy transformations. And then work is just defined as that force over a distance, right? So how long are we doing or exerting our force for? And then the main thing that we'll be focused on in this chapter, though, is heat. So kind of the flow, then, of energy then caused by difference in temperature. And so heat and work are just two different ways that an object can exchange energy. And so again, right, just kind of comparing other types of energy. So we have kinetic energy, so like we were thinking of our ball, or maybe, right, just like moving. And then this could also be the flow of electrons. So that's also kinetic energy. And then thermal energy is, like we said, again, associated with our temperature. So it's a form of kinetic energy, right? So based off of our temperature here. And so again, right, we have so two main types of energy, either kinetic or potential. So like we said, we're mainly caring about how much energy is stored within our bonds, or we can kind of think of it in the caloric sense, like hopefully you had lunch before coming here. Maybe you're consuming, right, some calories. And so again, right, there's potential energy in that food, which your body converts to hopefully some kinetic energy. So I'll highlight that. So the energy stored in those bonds. So just recap of our energy forms. So again, our kinetic, also light energy, but could also talk about, right, nuclear. So, right, you have kind of potential energy stored in that nucleus, and then boom, once that nuclear reaction happens, right, that gets converted to heat and boils water. So you just have fancy ways to boil water and then turn the turbines, and then compare to chemical. All right, so let's bring us to our kind of units of energy. And so even though I said, right, we probably don't need this formula, it comes up just so we can see where the units come from. So again, if you have taken physics, remember physics or anything, it's derived from this kinetic energy equals 1/2 mv squared. And then if you remember in physics land, mass is typically given in kilogram. So, right, our base unit is grams, but okay, physics is always in kilograms. And then velocity squared. So remember, velocity is measured in usually meters per second. So then you square that. Okay, so that gives us our units for energy. And so typically, the unit that you will work with is the joule. But just so you know where the joule came from, so again, those units are kilograms times meter squared over second squared. So just plugging the units into this formula, which is also equal to a Newton meter, again, if you were looking for this relationship. So we won't need this relationship in here. I don't think you'll need to reference this either, like I said, in this class. I feel like in my 200 level, they might want to know it, but you still might want to know it, again, just so you know, like, what the heck is a joule if you were ever doing some problem. That being said, I did make it through physics, right, through unit canceling, so this is helpful for physics. And then this works out to a joule of energy then is the amount of energy needed to move 1 kilogram mass at a speed of 1 meter per second. And then we have this unit called a calorie. Except, so we'll start off with, this is little c calorie. And so that's the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And then a food calorie is actually a kcal, or 1,000 calories, or 1,000 grams of water. So now time to get depressed. But if you were ever bored, though, you can think about how they would quantify that. Maybe you've even seen on YouTube people like running those experiments, right, where you like burn a chip and you try to like capture all the heat given off in the calorimeter. And so that is how you can calculate your food calorie. And right, that's how you would do kind of all these calculations. Now we're kind of getting to those calculations. Well, how do we quantify what a calorie is? What is that equal to? And then if, again, maybe you've taken other science classes, or you may have also heard our specific heat of water. So that's also related to this, right? So again, the amount of energy needed to raise 1 gram of water. So that would also be equal to 4.184 joules. And then without getting like too far down the rabbit hole, so I just want to have a quick reminder, right? This is why water acts as a big heat sink. So that's why, like, West Coast, Best Coast, but we're mainly temperature regulated by the ocean because, again, of this pretty large value of specific heat, how much energy it does take to boil water, or again, raise the temperature of water, or lower it for that instance. So again, right, the ocean kind of helps keep us pretty regulated there. So that's pretty nice. And then, so we could convert between these. So again, 1 calorie is related to 4.184 joules. Then we have a kilocalorie, or kcal, is 1,000 calories. And then big capital C food calorie, like you see on the box, is again a kcal, or 1,000 calories. And then kilowatt hour, if again you got bored and started looking at your electric bill and wondering about things, so that's equal to 3.60 times 10 to the 6 joules. So that's your kilowatt hour. And so we'll start off with our first law of thermodynamics. And so thermodynamics is just defined as the study of energy and its conversions. And so then the first law of thermodynamics is the law of conservation of energy. And so that means our total energy in the system is constant. So that means it's conserved. And so, right, the energy may change form, like it may go to heat, for instance, right? We may lose some as heat, but we'll still have that amount of energy conserved. And then the other thing that this gets into, I don't know, have you guys ever heard of those perpetual motion machines? So yes, I'm sure you may have heard of this kind of theory, but why it's just you can't actually make one. And so the idea is, right, can you have a machine that somehow feeds back into itself and keeps going forever? And this breaks the first law of thermodynamics, though, right? So we can't create extra energy without some sort of source there. I think that also gets into like machine efficiency too and conversion. But yeah, so we can't just make energy. All right, so let's look at what we'll look at. And so we're interested in kind of quantifying our, again, how much energy is either given off in like these exothermic reactions that we've hinted at, or maybe that they require. And so chemical reactions involve breaking and making new bonds. And so we can compare then the amount of energy costs. So it costs energy to break old bonds, and then we gain income from making new bonds, and that's thermodynamically favorable. And so the amounts that we're going to look at, kind of these general amounts, are called our bond energy, and they're calculated in the gas state. So again, right, there could be variations if it's not the gas state. And then for the most part, we have homolytic cleavage. And so let's just talk about what that is. And so homolytic, and this is typically what we do see, but that's where each atom gets half of your bonding electrons, right? So if you have the CH bond, and then you can use these single arrows to show homolytic splitting, so they each get one electron. And so this is compared to, if I could spell heterolytic, I probably misspelled it. So heterolytic means that only one atom gets them. And so this is a more specialized bonding scenario, but again, I just want to go over the definition. And so you could have this weird bond, and it's typically found between boron and nitrogen, and so you can see why, right? So boron was already odd to begin with, since it only has 3 valence electrons, so it can only make 3 bonds, typically speaking. But then we see how it makes a 4th bond from this strange heterolytic bond. And so let's kind of look back where this came from. And so if you draw our ammonia Lewis dot structure, well, it has this one lone pair on top. And so that's what's forming this bond here. And so if you were to split this apart, this would be heterolytic cleavage, where they would go back to where they originated from. And so nitrogen would get 2 electrons. But like I said, this is pretty rare, but I at least want you to be aware that, like, yes, there are two different types, so it's not always homolytic, but typically, yes, we do look at just homolytic bonding scenarios. And then that being said, this is a cool area of research. This can get into like frustrated Lewis pairs and all sorts of cool stuff because of this like boron and anything that can start to donate electrons like nitrogen typically. All right, so again, actual bond energy will vary, but we can still use our average bond energy from these tables, or maybe I'll provide them on the exam to get our delta H, which stands for our change in enthalpy, which is again just our exchange of heat, right? So is it exothermic? Is it endothermic? And we'll go over what that means. And so starting to get into it, so like we said, bond breaking requires energy by our thermodynamic definition. So it's formally positive, and so that's considered endothermic, meaning it requires energy. Versus anytime you make a bond, that's considered to be thermodynamically favorable, so it's going to lower our energy levels. So that gives us back energy, so it's exothermic, so negative in value. And so what we can do is we can sum up the total of our bonds broken, add them to our bonds formed, and so again, right, bonds broken will be positive, so putting energy in to break those bonds. Bonds formed will be technically negative. Add those two and see which one is greater, right? Are we putting more energy in? Are we getting more energy out? And that tells us overall, again, if that reaction is exothermic or endothermic. And we'll still talk about what that means. Okay, before we take a break, let's just look at our general trends, at least in bond energy. So I think we've said a couple of these things before, but kind of recurring themes. So again, in general, the more electrons they share, the stronger the bond. So right, we kind of went over that. So we said single bond was the weakest, triple bond is the strongest. And so now that's reflected in these numbers. So for example, carbon nitrogen is 305 versus this carbon nitrogen triple bond, which is 891. So same thing, compare your carbon triple bond to your single bond, so your single bond is weaker. So again, just like we expect. We also have this generalization. So the shorter the bond, the stronger the bond. So right, if they're kind of shorter, they're held together, so greater electrostatic charge. So charge is divided by the radius, so radius is small, that gives us stronger bond. And so we see that. So just basing off of our general trends. So fluorine is the smallest, and so it has the highest energy of 237 versus this bromine, which is 193. So again, just general trends. And so bonds, again, just tend to get weaker down the column. Makes sense, right, as we have more onion shells. And then stronger across the period, right, as they get more electronegative, kind of pull them in closer as well. And so on an exam, I'll probably just give you like the specific bond you're looking at, but if you're doing homework, then you can just reference kind of any table. The only thing to watch out on is make sure the units are either the same, or if you're in a different table, just tell me what unit you're in so I can convert later. And so typically though, we want to be in kilojoules per mole, so looking at our bond energy, so that's what these are all in. So, you can take that in, kind of appreciate those trends. And then the special one is down here. And so for our sake, we're probably always going to want to use the 799 number. So this is for the bond strength in CO2, so the molecule. And so that's compared to this number, right? Just a regular C. double bond oxygen like in acetone or something. So this would be in just a regular compound. But use this number slightly higher for CO2 there. All right, let's take a break though. And then once we come back from like our 10-minute break, then we'll go through this kind of change some more. All right, now we're back. All right, any questions come up? All right, so let's go through this first reaction here. And so what we're trying to do is we have methane plus chlorine gas. Do you have a question or anything I can help with or? All right, just like I said, just let me know what questions we have. We can always go over anything. And so we're looking at this reaction of methane plus chlorine gas. And so it kind of walks us through this process, right? So we have to put energy in to break those bonds. And let's add some numbers to this, right? They just have our little graphical reference. But okay, let's look this up. And so I'm just interested in what we're breaking, right? So we're kind of looking at what happens. So we need to break a CH bond. So that's a single bond. And then we can go up to here. Okay, well that's worth 414. And that would be, right, kilojoules per mole, but we have 1, so okay, just kilojoules there. And then we also need to break our chlorine-chlorine bond here. So let's look at what that is. So chlorine-chlorine down here, so 243. So putting all that energy in. All right, so let's total that up. Don't have my calculator ready. That sounds right. Yeah, you're right. I shouldn't have pulled out my calculator. All right, so 657. So, okay, that's what we put in. So let's compare that to what we get back out now. And so there's, right, basically our transition state. Now we need to make our carbon-chlorine bond. So that's what we get back out. And so I'll put our little make category. And let's look up our carbon-chlorine bond. So that's 339 kilojoules. And then we also make this hydrogen-chlorine bond, so 431. And so first I'll add them up. And I guess we could have also done our math. So 770 kilojoules. And now that's back out, right? So I put a big negative sign. And then we want to add these two numbers together to get our overall energy of the reaction. And so I'll do 657 minus 770 to do that. And so that means that our reaction overall gave back negative 113 kilojoules. And so when it's negative, it tells us that the reaction is exothermic. And then to us, right, since it's releasing heat, so then we're kind of feeling it, we're the surroundings, so it would feel hot to us. As again, right, energy is released, we feel it, so it's kind of like the opposite almost. Does that make sense? Any kind of questions on that process? So let's kind of repeat this, and I may have to scroll around, or I'll let you copy the equation. So let's look at this combustion reaction. So burning methane, so CH4 plus 2 equivalents of water, H2O, give us 4 equivalents of H2. and 1 of carbon dioxide. And so like I said, I'll kind of let you try this out, but some hint that you might want to do is like really sketch these out, right? They don't have to be like correct in terms of geometry. It's just like put the lines together. What do you have to break, right? Like how many of those bonds do you have to break? And then compare that to the equivalents that you're making, like this 4H2, for instance. So copy this. I'll scroll back up to this table for now. If you need me to go back to the reaction, I can, but try that out for a few minutes, and then we'll go over it together, see how we did. Volume. All right, so I've just sketched it out. And so it looks like we have to break a lot of bonds, right? So we have to break all 4 CH bonds, correct? So I'll start with that. And so I always like separating them. So let's figure out what we're breaking. So 4 CH4s. So let's go back to the table. So CH is 414 times 4. So we have 1656 so far. And then we also have to break all these hydrogen-oxygen bonds. And this is tricky, so that's why I said, right, sketch this out. Because how many of these do you have to break? 4. Yeah, so good, right? So you want to, again, draw it out, count it out, so you're really Sure. So 4 OH bonds. Let's see how much each one of those is worth. So 464 times 4 again. All right, so 1856 for that process. All right, so that gives us, let's add those two together. So figure out how much total energy in. So that's 3,512 kilojoules in so far. I'll put a big plus sign so we remember. So let's figure out how much we get back out from making bonds. And so again, that's why I said draw it out. So 4 equivalents. So we have 4 HH bonds to start off with. Single bonds. So that's 436 times 4. Oops. So 1744 kilojoules. Then we had the CO2, right? 1 equivalence, but 2 CO double bonds. And this is where you use the special 799 number. So now 2 CO2 bonds. So 799 times 2. And then again, add those all up. Well, let me do this piecewise. So that gives us about 1598 for that. Let's add those numbers now. And so again, this is energy out now, so I'll put a negative sign. So negative 3,342 kilojoules out. And then, so what about the overall process, right? So what do we think? Add those two together. You can probably already tell which one's going to be higher. So 3,512 plus a negative 3,342 to give us overall 170. So our overall change in enthalpy, and so that's this little symbol, right? Change in enthalpy, how much heat was exchanged. So it was positive 170 kilojoules, which means that this reaction was endothermic, so it required energy. And so to us, this reaction would feel cold. Oh, I don't know why. And you can think about like a ice patch. That's like a typical endothermic reaction. So typically that's ammonium chloride. And then to dissolve ammonium chloride, it takes energy. So that's why once you bust that seal, right, you release the water and then it starts dissolving and then it feels cold to you because your body is supplying the heat to get that endothermic reaction to go. So same thing, if you were holding this reaction flask, right, it would feel cold, or perhaps even, right, well again, it's a combustion, so it's going to require some reaction, some energy to get going for this one. And so question, so why does making bonds release energy? So this is from like a thermodynamic standpoint. This kind of maybe goes too far beyond, but just like thinking two atomic orbitals. So you have hydrogen and hydrogen, and when they come together to make a bond, that makes this like favorable bonding scenario. And so that's sort of like bonding, favorable bonding is what gives that formal energy release. But like I said, that might be too beyond the scope. But and then that's like not to be confused with like endergonic processes. So that's like completely different, but that does get into like the energy of metabolics, and it's actually quite fascinating, like how your body, right, has a ADP cycle to power itself. Anyways, that's like way too beyond this course now. All right, so let's look at some diagrams. And so we have these diagrams to just kind of show us which way the energy is going. And so we have an exothermic process. And so again, overall energy is negative. And so we could have a simple diagram like so. So reactants, right, are higher in energy compared to our products overall. And then this diagram is just showing right where the energy is going. So this is why I keep saying, okay, it feels hot to us though, right? So that negative energy has to go somewhere. So then again, if you were standing next to it, okay, that would feel hot to you. This is another way to write this, and you'll probably be expected to draw this on the exam or label it or like calculate the parts appropriately. So that's on all versions of the exam, online and in person. And so for our exothermic reaction, so again, reactants start off higher than our products. So our change in energy that we calculate is our difference from products to reactants. So again, that's how much energy is released. So that could be given on an exam, like, okay, if you have a reaction that released 40 kilojoules of heat or something like that, right? You might have to draw the diagram and label it. And then this energy here is our EA, or our activation energy. And so that could be on the exam too. Okay, this reaction has an activation energy of 30 kilojoules. And so you would just write, kind of label that on your diagram. So activation energy, so it's your reactants to this transition state. And so your transition state is just this like fleeting state where things are coming on or off. So again, this is kind of like beyond our scope of the class, but let's say you're doing, some reaction, maybe changing a halide off. And again, this is like already getting too much into the scope of things. But this is just kind of an example, right? The short fleeting state where it's releasing one element and then binding another. And so that's our transition state. And then again, ending in our products there. And then we have progress of our reaction. So this is usually time or something. And then energy on our y-axis. And then endothermic is pretty similar, just opposite. So again, we could show it this way. So our products are higher than the reactions in energy, right? If again, we're putting energy into the system with our endothermic process. We again use this diagram to show the energy flow. So if the system is overall positive, right? Well, we have to get the energy from somewhere. So that's where this will again feel cold to us if we're feeling an endothermic process occur. So your energy has to flow. And again, similar, but slightly different, right? So now our reactants are lower than our products. So activation energy is again from the reactants to your transition state. Your change in enthalpy is your products from your reactants. And again, just be expected to label these, draw these, some sort of thing on the exam. Okay, we're like flying through this chapter, I think. And then again, we're kind of just like touching on things in here. And so we just want to like briefly touch on kinetics and just like at least vaguely talk about some factors. We're not going to get into quantifying this or anything. Uh, if you were interested, right, that's what 200 level chemistry is for. And so the speed of a chemical reaction is called its reaction rate. And so that's just the measure of how fast the reaction either makes products or uses reactants. This gets into all sorts of things too. So this is something that has to be measured, but then how you measure that kind of gets into like this statement. And again, like I don't want to get too far down the rabbit hole, but that's like the fun part of chemistry is like, well, how do you measure these species? And it could be like UV spectroscopy. I can't remember if I don't think we do a spectroscopy lab in here. I don't know if you've ever just like taken the absorption of like dyes and stuff on those little like UV spectrophotometers, like the rainbow spectrum things. Maybe yes, no. Do you do this in high school? Well, basically, like you have the light going through it and you see what wavelength it absorbs. Yeah, so maybe we've done that. That's kind of what I mean. So depending on what your species is, you can use that technique to monitor. That's also like you could use again like mass spec, NMR. Those are the main ones. But again, that's the fun part. Okay, well, how do you measure this reaction? That gets into again more like chemistry and the whole research thing and how do you actually physically measure these things? Is it continuous? Is it sampling? Blah blah blah. I mean, I go blah blah blah, but there's so much behind it, and that's really the beauty of a lot of chemical papers. Is just kind of way too beyond this scope. And then with that, and again, a lot of time and research is also put into like how to control these chemical reactions. And this could be anything from like how do we figure out this organic mechanism and maybe tune some sort of synthesis or tune some sort of process. Or you could think of like the big industrial scale, hey, how do we keep this flowing and like efficiently pumping out product and, you know, at reasonable energy costs. So all these sorts of things, right? Wide range of what this means to control a chemical reaction. Or again, thinking back to like grad school, we don't want like a runaway reaction either. Like what if it's extremely like it picks up and it like goes out of control, it starts heating up, like you might have to have a bath to cool it down. There's all sorts of considerations. It just, like I said, depends on what you're looking at. And so again, just kind of like really broadly speaking, for our 100 level purposes, well then we can imagine some factors that might affect our reaction rate. And so our concentration can affect the reaction rate. I actually forgot what lab we're doing. So I think we'll see that this week. I'm trying to remind myself of the lab before I say it. Yeah, so we'll be looking at like concentration, that's right. So we do compare our concentrations of acid this week. So we'll compare how fast it takes to dissolve our magnesium with 1, 2, and 3 concentration. And so as you'll see, right, the greater the concentration, the faster the reaction. But that kind of makes sense, right? You have more molecules to literally like react faster. And so more molecules increases, right, our frequency of those collisions and frequency of both amount of collisions. And well, technically they have to be like successfully oriented, but again, more collision just means more successful orientation as well. And that, if you're interested in that, that's like physical PChem research, right? So you can do oriented molecule research, like shoot 2 molecules down a tube, switch sides and all these things and figure out how much energy that takes, right? The minimum energy to actually get a reaction. And so that's again where orientation comes into play. So with that, concentration is also related to gases. So higher the pressure or partial pressure would also mean higher concentration, so quick and the faster things will react. And then again, in our world, right, we're mainly looking at molarity for solution concentration. And then, like I said, we're not going to quantify this. If you want to quantify it, take my 200 level series. Otherwise, we'll just kind of generally say that if we increase the temperature every 10 degrees Celsius, that roughly doubles the reaction. But again, that's very general. So obviously, right, increase the temperature, then we increase the rate of reaction. So increase temperature, so faster collisions, right? Or with that kind of more energy to make those successful collisions. So again, going back to that P chemistry research, right? If you're trying to figure out kind of the minimum activation energy for that orientation, well, higher temperature gives you higher energy, right, for those collisions. And so this does tease the Arrhenius equation. Maybe you guys have even heard about it if you've taken chemistry before, but like I said, we're not really going to look at that in here.
So with that tendency, with the reaction doubling, is that like logarithmic, or it's just?
It's like just super general. Yeah, the Arrhenius equation would be better, although, I mean, now that you say it, like maybe it does have a logarithmic trend, but yeah, we just don't get into the math that deep at this level. All right, so kind of other points in this chapter. And so we can touch on catalysts. And so I think you guys caught on to catalysts pretty quickly in here. So right, we looked at our potassium iodide in our hydrogen peroxide decomposition reaction. And so that helped us define what a catalyst was. And so we said that they are substances that affect the rate of the reaction without being consumed. We even saw, so I should have written it probably better. Right, we could write it over here. We might have a loading percent. I'm just like making up stuff right now, but sometimes you'll say like how much catalyst you use, like 5 to 10% loading. That's what that would be if you saw that in a paper. And then again, made water. Yay. And so also chemists usually talk about catalyst, so we usually mean like a positive catalyst, so that means it's going to increase the rate. For those biologists in here, what's a catalyst called that decreases the rate? Remember that term? So inhibitor. So an inhibitor slows the rate. So usually it's something that interferes, right, and kind of gets in the way. Catalyst usually works by providing some sort of alternate mechanism. And so let's look at actually some catalysts, especially since we're running probably fast on time here. And so we'll look at this Grubbs catalyst. And so this was a pretty big deal, at least in the world of chemistry. So it won the Nobel Prize back in 2005 for this work. So that was Grubbs, Schrock, and Chauvin. And so, okay, well, why was this so cool? And again, what we're trying to get at is this creates a completely different mechanism. And so these cool catalysts do what's called olefin metathesis. And so they just like make these bonds. I'm trying to find a better example, but you can kind of see how it just shows the intermediate, but it binds these substances so that they go on to do these cool bond transformations. And so again, it's providing an alternate pathway though, because we have the metal And then it can bind to the metal and do its transformation. Here's a better reaction. And so this is what's going on. So it kind of does this cyclization and then makes ethane in this case, ethene, right, the double bond ene. And so again, right, whole point is completely different pathway. This wasn't there before, and you can't just like react this and have it do this, right? So it's this ring closing mechanism, and then it kicks this group off. But by providing a whole new pathway through this metal, then you can do it. And so then, right, you can also get a taste for how they write reaction conditions shorthand. So this one, for some reason, also has some copper chloride in there. Right, this one, I think it's implying 0.2 molar, maybe like equivalence in loading. Oh no, I don't know what that means. But it does say 0.05 equivalent, so that's pretty low, right? So that's how much catalyst you need. So you can tell reaction conditions. And so again, in chemistry, we're always talking about making a reaction faster, or maybe in the case of like the olefin metathesis reaction, that reaction basically doesn't happen without a catalyst. And so this is an example. So this reaction of ozone plus this oxygen radical gives us O2, and this is pretty slow. And then just showing how this mechanism is catalyzed by this chlorine radical. And so this is kind of teasing a little bit of atmospheric chemistry too, so that's where you get a lot of radicals. And then again, key part, catalyst is consumed and then reformed, right? So there's our catalyst in the beginning and the end. So that's not a typical way to write it out. Like we saw, we usually write it over the arrow, but if we write it like this, we see, okay, it's the same in the reactants and the products. And so this is just kind of another good visual, so trying to just show us, again, thinking about the olefin metathesis, maybe the reaction has a really high activation energy or transition state that's hard to reach for whatever reason, energetically speaking, and then it essentially creates two smaller reactions. Again, kind of going back to this, it's like, okay, we have one step of it forms here, and then the metal's going to continue and kick this off, right? So kind of two separate, or maybe even multi-reactions, right? We don't have a full mechanism here, so we don't have a full sense of what's going on. So maybe there's even multi-transition states, and again, that's kind of the beautiful thing that's covered in a lot of chemistry papers, is it might try to go through those transition states. And again, main point, that it lowers our activation energy, creates more steps, different pathway, and then we get to our product. And then other things to kind of think about is, okay, well, we have two different types of catalysts. So we have what are called these homogeneous or homogeneous catalysts. And basically this means all species present in the same phase. So that would be like the Grubbs catalyst, or any sort of, so this is, I call it like, this was my vein of research, where you like try to make just things that are, this usually all happens in either like organic liquids, usually, because everything's air sensitive. But, right, they're all just like in solution typically. And so this is a lot of chemistry too. So I'll just call this the entire vein of organometallic. And so that's kind of compared to these heterogeneous catalysts, which I often say are kind of more like industry catalysts. And well, let's look at why. And the definition is a species present in a different phase. And somebody's already named it before, but what's a typical catalyst that a lot of people use every day that's in two different phases? Guesses? Somebody brought it up, asked a question about it too. Like, I don't even know. Your car catalytic converter. Yeah, I knew you would. As soon as I said it. So yeah, your car catalytic converter is your heterogeneous catalyst that you're familiar with. So like we'd mentioned, it's typically some like palladium platinum catalyst there. And so that's going to be in the solid phase. And then, right, it provides some sort of surface for obviously your gas to come along and react. And so now you can kind of guess why this is what I would call like more industry standard for catalysts is, again, it's easy to separate these, or right, so obviously your car metal stays the car metal and the gas goes on its merry way out your tailpipe. Or in industry, again, right, that would make it easy to separate, or again, maybe you're passing gas over a metal, so easy to separate. So the problem with these homogeneous catalysts is that it could be difficult to separate back out, especially like recovering that catalyst. So typically it gets like trashed for the most part. And so the Grubbs catalyst, that being said, is available commercially. So if you're using that, and that goes back to, right, the 0.05 equivalent. So that's pretty low loading. So that's good, right? Because again, if you're trashing it, well, that's the cost of doing business, again, versus a heterogeneous catalyst. So that's kind of, again, cost-wise, typically better. And then getting into like, if you're looking at the future and what area kind of interests you. So this is kind of more materials chemistry, I would call it, or even like pure inorganic research. So that's where you, like I said, get into these like materials. I'm not into this vein of research, like not to make fun of it, but typically what a lot of these synthesis goes like is like take this mixture of metals, bake the crap out of it for several hours and see what happens type of thing. But I mean, that's just typically the synthesis, or always trying to form some different like metal oxides or different materials. But yeah, that just different veins of research, but kind of depending on like your personal area of interest, right? One might call to you more than the other. Let's see what else. So well, I don't want to get too far deep. We probably want to save Le Chatelier's principle. So yeah, let's probably stop there for now, just because I don't want to start Le Chatelier's principle. No need to rush that. All right, so we'll save Le Chatelier's for Wednesday. We'll do our demo too, so I'll make sure we get some balloons filled to explode. And then just kind of trying to look at the homework, trying to mind myself. So yeah, we can probably go over the homework too, although I think it's a lot of what we've done, or at least so far, right? Bond making, bond breaking. So that doesn't look too bad. So yeah, you guys can probably sneak out of here a little early then. I think that sounds fine. And then, yeah, hang around if there are questions, but otherwise I'll see you on lab on Wednesday. So I think we've kind of flown through this chapter, but hopefully it should feel pretty okay for people. And then let me know online if there's any questions. Like I said, I think we're progressing pretty nicely in this chapter. And then on Wednesday, hopefully I'll be more caught up by grades. Thank you, thank you.